Imagine for a moment, gazing up into the velvety canvas of the night sky, far away from the city lights. You see countless pinpricks of light, each a distant star, a galaxy shimmering like a cosmic jewel. But what if the very stability and grandeur you perceive in these spinning colossal islands of stars is a profound illusion, held together by an unseen force, a silent architect whose existence challenges everything we thought we knew about the universe? Could the cosmos itself be hiding a secret, a phantom presence dictating the very dynamics of galactic motion, whose true identity remains one of the deepest puzzles in science? For centuries, our understanding of gravity, largely thanks to Isaac Newton and later Albert Einstein, has allowed us to predict with remarkable accuracy how celestial bodies should move. In a typical gravitational system, like our own solar system, objects closer to the central mass orbit faster, while those farther out move more slowly. Think of Mercury zipping around the Sun in just 88 Earth days, while Neptune takes a leisurely 165 Earth years. This same predictable principle, we once assumed, should apply to galaxies. The stars and gas clouds closer to the galactic center, where most of the visible mass is concentrated, should orbit rapidly. Those in the sparse outer regions, far from the central pool, should lag behind, moving much slower. If they didn't, the outward centrifugal force generated by their speed would simply overcome the gravitational pull of the visible matter, flinging them out into the cold, dark vacuum of intergalactic space, much like water droplets spinning off a rapidly rotating wheel. But that's not what we observe. Galaxies persist, their outer stars held firmly in place, defying our expectations based solely on what we can see. If galaxies don't follow these predictable rules, what unseen cosmic force then dictates their extraordinary ballet? The first faint whispers of this cosmic anomaly emerged in the 1930s from the keen observations of a Swiss-American astronomer named Fritz Zwicky. Zwicky was a brilliant, if somewhat eccentric scientist, known for his sharp intellect and blunt manner, working at the California Institute of Technology. He turned his attention to massive structures in the universe, specifically to the Coma Cluster, a sprawling collection of thousands of galaxies located about 336 million light-years from Earth. By carefully analyzing the light from these galaxies, Zwicky could measure their individual speeds as they moved within the cluster. This measurement relied on a fundamental principle known as the Doppler effect. Just as the pitch of an ambulance siren changes as it moves towards or away from you, the wavelength of light from a celestial object shifts depending on its motion. Light from objects moving away from us shifts towards the red end of the spectrum, redshift, while light from objects moving towards us shifts towards the blue, blue shift. By measuring these shifts, Zwicky could determine the velocities of the galaxies within the Coma Cluster. What he found was perplexing. The galaxies within the cluster were hurtling about at astonishing speeds, far too fast to remain gravitationally bound together by the visible mass alone. Using a concept called the virial theorem, which relates the kinetic energy of motion, of a system to its potential energy due to position, in this case gravity, Zwicky calculated the total mass required to keep the Coma Cluster from flying apart. His calculations revealed a staggering discrepancy. The cluster needed to contain about 400 times more mass than could be accounted for by the visible galaxies. He concluded, quite boldly for his time, that there must be a vast amount of unseen non-luminous material contributing to the cluster's gravity. He famously referred to this missing mass as dunkle Materie, or dark matter. his findings were revolutionary, but perhaps too far ahead of their time. The idea of such an enormous amount of invisible matter was met with skepticism and largely faded into the background of astronomical discourse, perhaps due to Zwicky's abrasive personality, for several decades. But how could such a revolutionary concept, proposing 400 times more unseen mass, simply vanish from scientific discussion for decades? It wasn't until the 1970s that the concept of unseen mass resurfaced with undeniable force, thanks to the meticulous and persistent work of a remarkable astronomer named Vera Rubin. Working at the Carnegie Institution of Washington, Rubin, along with her colleague Kent Ford, embarked on a groundbreaking study of galaxy rotation curves. A rotation curve is essentially a plot that shows the orbital speed of stars or gas clouds within a galaxy as a function of their distance from the galactic center. To measure these curves, Rubin and Ford used powerful spectrographs attached to large telescopes, similar to how Zwicky measured the Doppler shift, but this time focusing on the intricate motions within individual spiral galaxies. Vera Rubin chose to study Andromeda, our closest large galactic neighbor, and then systematically examined a collection of other spiral galaxies, including NGC 3115, a lenticular galaxy, and many others. She painstakingly measured the Doppler shifts of emission lines from hydrogen gas clouds and absorption lines from stars at various distances from the galactic core. Her expectation, based on the visible distribution of matter, was clear. The rotation curves should show a decrease in orbital velocity for stars and gas clouds farther from the center. The vast majority of a galaxy's visible mass, after all, is concentrated in its bright central bulge and luminous disk. So, just like planets in our solar system, outer stars should experience a weaker gravitational pull and thus orbit more slowly. However, what Vera Rubin consistently observed across dozens of galaxies was profoundly different and utterly perplexing. Instead of the expected decline in speed, the rotation curves remained remarkably flat. Stars and gas clouds located at the very fringes of these spiral galaxies, far beyond the regions where most of the light originates, were orbiting at speeds nearly as high as those closer to the galactic core. To put this into perspective, imagine a cosmic merry-go-round, but instead of the horses closer to the center moving faster and those on the edge moving slower, all the horses, regardless of their distance from the center, are moving at roughly the same high speed. This simply should not happen if the only gravitational force at play comes from the stars and gas we can see. Why were these distant stars clinging so stubbornly, so mysteriously, to their speedy orbits? The implications were inescapable and startling. If the outer stars were moving at such high velocities, yet were not flying off into space, then there had to be a significant amount of additional invisible mass, providing the necessary gravitational glue. This unseen mass, whatever it was, had to extend far beyond the visible boundaries of the galaxy, forming a vast spherical halo that enveloped the luminous disk, stretching for hundreds of thousands of light years. Rubin's calculations indicated that this mysterious, non-luminous matter must outweigh the visible stars, gas, and dust by a factor of at least 5, and in some cases, up to 10 times. Her meticulous observations and the consistent results across numerous galaxies provided the definitive, compelling evidence that Zwicky's dark matter was not just a statistical anomaly in a distant cluster, but a fundamental, pervasive component of individual galaxies themselves. This profound discrepancy presented a stark choice for astronomers. Either our understanding of gravity was fundamentally flawed, or the universe contained an enormous amount of matter that we simply could not detect with our telescopes. The latter explanation, while radical, seemed the more plausible path forward, given the robustness of gravitational theory over centuries. Thus, the concept of dark matter transitioned from a speculative idea to an essential component of our cosmological model. It became clear that the visible universe, the stars, planets, nebulae, and galaxies we admire, is merely the luminous tip of a much larger, unseen iceberg. The phantom skeleton, the invisible hand, guiding the graceful yet bafflingly fast pirouettes of galaxies, had revealed itself through its gravitational signature. This realization opened up a new frontier in physics and astronomy, challenging us to understand the true composition of our universe and the nature of this pervasive yet elusive cosmic architect. What then is this ghost of the cosmos, whose pervasive presence utterly dominates the universe? After traveling through the cosmos to witness the perplexing behavior of galaxies, observing stars stubbornly clinging to their orbits against all visible odds, we now turn our attention to the invisible force behind this cosmic ballet. We have seen the hand of something unseen, a gravitational presence that defies our understanding of what makes up the universe. This brings us to the profound question: what exactly is this dark matter? And what role does it play beyond simply holding galaxies together? To understand dark matter, it is crucial to first understand what it is not. Our everyday experience, and indeed the vast majority of astronomical observations, concern what scientists call baryonic matter. This is the familiar stuff of the universe: protons, neutrons, and electrons. It is what forms atoms, which then combine to create molecules, and eventually all the structures we can see and touch, from the smallest speck of dust to the grandest galaxy. Stars, planets, gas clouds, even you and me, are all made of baryonic matter. The defining characteristic of baryonic matter is its interaction with light, or more broadly, with the electromagnetic force. Protons and electrons carry electric charges, which means they can emit light when heated, absorb light when struck by photons, or reflect light from their surfaces. This constant give and take with light is precisely how we observe the universe. Every telescope, from radio to gamma ray, relies on these interactions to gather information. If it doesn't glow, doesn't absorb, and doesn't reflect, how do we ever hope to glimpse the utterly invisible? Dark matter, however, participates in none of these electromagnetic dance steps. It does not emit light, so it doesn't glow like a star or nebula. It does not absorb light, so it doesn't cast shadows like a dust cloud. And it does not reflect light, so it cannot be seen by bouncing a beam off it, much like trying to see a ghost with a flashlight. Imagine an object that is utterly, perfectly transparent across the entire electromagnetic spectrum. From the longest radio waves to the shortest, most energetic gamma rays, it is truly invisible, a phantom presence that passes through everything without leaving a trace of light or shadow. This fundamental lack of electromagnetic interaction is why it is called dark, not because it is literally black, but because it is utterly undetectable by any form of light, or indeed by any of the four fundamental forces of nature except for one. The solitary interaction dark matter engages in, the only way it reveals its presence is through gravity. It possesses mass, and anything with mass exerts a gravitational pull, warping the fabric of space-time around it. This gravitational influence is precisely what Vera Rubin observed in her studies of galaxy rotation curves. The mass of the dark matter creates a gravitational field strong enough to keep stars orbiting at high speeds, preventing them from being flung into the cosmic void. Imagine trying to steer a car around a sharp bend. If you go too fast, you'll skid off the road. For stars at the outer edges of galaxies, their orbital speeds are so high that based on the visible matter alone, they should have long ago skidded out of the galaxy. Yet, they remain firmly bound, held in place by an unseen gravitational anchor, the dark matter halo enveloping the galaxy. This sole interaction, gravity, might seem subtle, but its influence is profound and widespread. When scientists tally up all the mass and energy in the universe, they arrive at a surprising cosmic recipe. Only about 5% of the universe is composed of the ordinary baryonic matter that makes up everything we can see and interact with. An even more astonishing 68% is attributed to dark energy, a mysterious force causing the accelerated expansion of the universe, a topic for another exploration. This leaves a staggering 27% of the universe's total mass energy density accounted for by dark matter. This means that for every kilogram of stars, planets, and gas that we can detect, there are approximately 5 kilograms of dark matter lurking unseen. It is a dominant component of the cosmos, dwarfing the familiar matter that forms galaxies and stars. Could we be living inside a colossal unseen structure, whose true scale and composition we've only just begun to fathom? Think of it this way. If all the visible matter in a typical galaxy like our Milky Way were represented by a sprawling metropolis, the dark matter would be an invisible, sprawling underground infrastructure. Vast subway tunnels, water pipes, electrical conduits, and deep foundations that constitutes the overwhelming majority of the city's weight and structural integrity, even though no one ever sees it. This unseen mass is not confined to individual galaxies. It forms a vast, intricate, and interconnected network throughout the cosmos, known as the cosmic web. Imagine the universe not as a uniform, evenly distributed soup of matter, but as a colossal, three-dimensional spiderweb stretching across billions of light years. This cosmic web is the fundamental scaffolding upon which all large-scale structures in the universe are built. It consists of vast, elongated filaments, where galaxies are strung like pearls on a necklace, massive nodes or clusters where these filaments intersect and galaxies congregate in their thousands, and enormous empty voids where galaxies are scarce. And at the very heart of this immense, invisible architecture lies dark matter. The formation of this cosmic web is a story that begins shortly after the Big Bang, the universe's birth. In the very early universe, matter was distributed remarkably smoothly, though with minuscule, almost imperceptible variations in density. These tiny fluctuations, however, were the seeds of all future cosmic structures. Because dark matter interacts only through gravity and not with light, it was able to begin clumping together much earlier than baryonic matter. Ordinary matter, with its charged particles, was still tightly coupled to radiation, photons pushing against electrons and protons, preventing it from collapsing under its own gravity. It was essentially held aloft by the intense radiation pressure of the young, hot universe. How did this silent, unseen architect orchestrate the grand design of the universe from its very inception? But dark matter, impervious to light, was free to respond solely to gravity. Over hundreds of thousands of years, as the universe expanded and cooled, these initial tiny density fluctuations in the dark matter distribution grew. Denser regions of dark matter slowly but steadily accumulated more dark matter, forming vast, diffuse halos and long, thread-like filaments. These were the first structural elements of the universe, an invisible skeleton that preceded the formation of stars and galaxies. Then, about 380,000 years after the Big Bang, the universe cooled sufficiently for electrons and protons to combine and form neutral hydrogen atoms. This pivotal event, known as recombination, had a profound consequence. It decoupled baryonic matter from radiation. Suddenly, ordinary matter was no longer held back by light pressure and was free to fall into the pre-existing gravitational wells carved out by the dark matter. Baryonic matter, now unhindered, began to collect within these dark matter halos and along the dark matter filaments. Over billions of years, these concentrations of ordinary matter grew denser, eventually igniting to form the first stars and then assembling into galaxies. So the cosmic web is essentially a dark matter web. Galaxies and galaxy clusters are not randomly scattered throughout space. Rather, they are embedded within and trace out the intricate patterns of this invisible dark matter scaffold. The largest structures we observe today, superclusters of galaxies spanning hundreds of millions of light years, are all shaped and held together by the overarching gravitational influence of dark matter. Without it, the universe would likely be a much emptier, more uniform place, possibly devoid of the grand luminous structures we marvel at through our telescopes. Dark matter is not merely a component of galaxies. It is the fundamental architect, the silent, invisible force that dictated the very formation and arrangement of the cosmos on its grandest scales. Its presence is a testament to the universe's hidden depths, suggesting that much of what truly matters remains beyond our direct perception, acting as the phantom skeleton that holds everything together. The initial observations of rapidly spinning galaxies, where stars at the edges moved with puzzling swiftness, were more than just an anomaly. They were the first tremor of a profound discovery. This whisper of an unseen influence, first noted by Fritz Zwicky in the Coma cluster, and later meticulously confirmed by Vera Rubin across countless spiral galaxies, opened the door to a deeper understanding of our universe. What began as a gravitational riddle quickly evolved into a quest to unmask a cosmic ghost, a substance whose presence is felt but never seen. Humanity's journey to comprehend this phantom skeleton of the cosmos relies not on direct sight, but on a collection of indirect yet compelling astronomical clues, each one adding another brushstroke to the portrait of dark matter. What extraordinary cosmic spectacles offer us a window into the presence of this hidden entity? Beyond the spinning galaxies, one of the most powerful and visually striking pieces of evidence comes from a phenomenon known as gravitational lensing. Imagine peering through a pane of incredibly thick, distorted glass. The images on the other side would appear stretched, magnified, or even multiplied. In space, gravity itself acts like such a lens. Any object with significant mass, whether it is a single star, a galaxy, or an entire cluster of galaxies, warps the fabric of space-time around it. When light from a much more distant galaxy passes through this warped region, its path is bent, just as light is bent when it passes through a conventional glass lens. The greater the mass of the foreground object, the more pronounced the bending effect, and the more distorted the background images become. Astronomers use powerful telescopes, such as the Hubble Space Telescope, to meticulously observe these cosmic distortions. They photograph vast galaxy clusters, which are colossal collections of hundreds or even thousands of galaxies bound together by gravity. These clusters are immense structures, often spanning many millions of light years across. When scientists analyze the distorted shapes and positions of background galaxies lensed by these clusters, they can precisely calculate the total amount of mass present in the foreground cluster. What they consistently find is astonishing. The gravitational lensing effect is far stronger than what can be accounted for by all the visible matter, the stars, gas, and dust within the cluster. This discrepancy tells us that there must be a significant amount of invisible mass contributing to the gravitational pull, distorting space-time and bending light to the observed degree. This unseen mass, which outweighs the visible matter by a factor of 5 or more, is precisely what we call dark matter. Gravitational lensing therefore serves as a giant natural cosmic scale, weighing the universe's invisible components. What cosmic lens could bend light so profoundly, revealing masses far greater than all the stars and gas combined? Perhaps the most direct and visually compelling evidence for dark matter comes from observing a spectacular cosmic collision known as the bullet cluster. This system, located about 3.7 billion light-years away, is the result of two galaxy clusters that have passed through each other. It provides a unique opportunity to see how different components of cosmic matter behave during such a dramatic event. When these two immense structures collided, their constituent parts reacted in distinct ways. The individual galaxies, made up mostly of stars, are relatively sparse. The distances between stars are so vast that most galaxies simply pass through each other like ghosts, largely unimpeded. However, the hot gas within each cluster, which constitutes the majority of the visible mass of a cluster, behaved differently. This gas, heated to millions of degrees Celsius and emitting X-rays, interacts electromagnetically. As the two clouds of hot gas from the colliding clusters slammed into each other, they experienced friction and slowed down, much like two waves crashing. This created a shockwave and caused the gas to become concentrated in the center of the collision. Telescopes sensitive to X-rays, such as NASA's Chandra X-ray Observatory, can map the distribution of this hot gas, showing it pooled in the central region between the two main clumps of galaxies. Crucially, scientists then used gravitational lensing to map the total mass distribution of the bullet cluster. By observing the distortions of background galaxies, they could pinpoint where the bulk of the gravitational pull was located. The result was a dramatic revelation. The regions of highest total mass were found ahead of the slowed down hot gas, coinciding instead with the locations of the individual galaxies that had largely passed through each other. This separation is the smoking gun for dark matter. The ordinary, visible matter, the hot gas, had been slowed and concentrated by electromagnetic interactions during the collision. But the dominant gravitational mass, the dark matter, had simply sailed through, interacting only gravitationally and not with itself or the gas. This observation powerfully demonstrates that the majority of the mass in these clusters is not ordinary matter, but rather an invisible substance that behaves differently, confirming dark matter's distinct and non-interacting nature. How could the visible matter and the gravitational center of these colliding giants become so dramatically separated? Moving beyond individual clusters, dark matter's influence stretches back to the very dawn of the universe, leaving its imprint on the most ancient light we can detect, the cosmic microwave background, or CMB. This faint glow bathing the entire sky is the afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. At that incredibly early stage, the universe was a hot, dense plasma of particles and light. As it expanded and cooled, electrons and protons finally combined to form neutral hydrogen atoms. This event, known as recombination, allowed light to travel freely for the first time. And it is this primordial light, stretched and cooled by billions of years of cosmic expansion that we observe today as the CMB. When satellites like COBE, WMAP, and Planck meticulously map the CMB, they reveal not a perfectly uniform glow, but tiny, subtle temperature fluctuations across the sky. These variations are incredibly small, on the order of microkelvins, but they are profoundly significant. They represent minute differences in density in the early universe. Regions that were slightly hotter or colder, slightly denser or less dense than their surroundings. These tiny fluctuations were the seeds from which all the large-scale structures we see today, from galaxies to galaxy clusters, eventually grew. Here, dark matter plays an indispensable role. In the very early universe, ordinary matter was tightly coupled with radiation, meaning the pressure from light prevented it from clumping together effectively under gravity. It was essentially pushed around by photons. Dark matter, however, does not interact with light. It was free to begin clumping gravitationally much earlier, long before ordinary matter could. These early clumps of dark matter formed gravitational potential wells, invisible pockets of enhanced gravity. Once the universe cooled enough for ordinary matter to decouple from radiation, this ordinary matter then began to fall into these pre-existing dark matter wells. Without dark matter, the universe would have been too smooth at the time of the CMB emission, and gravity alone from ordinary matter would not have had enough time to form the vast structures we observe today. The specific patterns and amplitudes of these temperature fluctuations in the CMB are exquisitely sensitive to the universe's composition, and cosmological models that include dark matter precisely match these observed patterns, providing strong evidence for its presence and crucial role in cosmic evolution. What delicate imprints from the universe's dawn reveal the indispensable presence of this invisible scaffolding? This leads directly to the final overarching line of evidence: the formation of the universe's large-scale structure, often referred to as the cosmic web. Look out into the universe with powerful telescopes and you won't see galaxies scattered randomly. Instead, you'll find them arranged in a vast, intricate network. Immense filaments stretching for hundreds of millions of light years, studded with galaxy clusters at their intersections, all surrounding vast, empty regions known as voids. This web-like structure is the largest known organization of matter in the cosmos. How did this magnificent cosmic web come to be? It began with those tiny density fluctuations imprinted on the CMB. Over billions of years, gravity relentlessly amplified these initial irregularities. Denser regions gradually pulled in more and more matter, growing into the filaments and clusters, while less dense regions became increasingly empty voids. However, computer simulations of cosmic evolution consistently show that if the universe contained only ordinary matter, it would not have been able to form such a complex and clumpy structure within the observed timeframe of 13.8 billion years. The universe would appear much smoother and less structured than it actually is. When dark matter is included in these simulations, the picture changes dramatically. Dark matter's ability to clump early, unimpeded by radiation pressure, provides the essential gravitational scaffolding. These dark matter clumps and filaments formed first, acting as gravitational anchors. Ordinary matter then flowed into these pre-existing dark matter structures, much like water flowing into a pre-dug trench, eventually forming the visible galaxies and galaxy clusters along the dark matter filaments. Large-scale galaxy surveys, which meticulously map the positions and distances of millions of galaxies across vast cosmic volumes, confirm that the observed distribution of galaxies perfectly matches the predictions of cosmological models that incorporate dark matter. The cosmic web, therefore, is not merely a distribution of visible galaxies, but rather the visible manifestation of an underlying invisible dark matter skeleton that permeates and structures the entire universe. Could our entire galactic neighborhood be merely the luminous frosting on a much larger unseen cake of dark matter? In summary, from the puzzling rotation of individual galaxies to the colossal collisions of galaxy clusters, from the faint echoes of the Big Bang to the grand architecture of the cosmic web, multiple independent lines of evidence converge to paint a consistent and compelling picture. Dark matter, though invisible and mysterious, is the indispensable gravitational glue, the phantom architect that has shaped and continues to govern the universe on its grandest scales. These observations tell us that dark matter exists and how it influences the cosmos, but they do not yet reveal what it is. The quest to understand its true nature continues, driving scientists to explore the very boundaries of our knowledge. If we know it's there and what it does, what fundamental particle could possibly be so elusive, yet so pervasive? Having observed the profound gravitational footprint of dark matter across the cosmos, from the anomalous rotation of galaxies to the bending of light around colossal clusters, the scientific community faces a compelling next frontier: understanding what dark matter actually is at its most fundamental level. We have seen its effects, how it shapes the universe's structure, and how it holds galaxies together, but its true identity remains shrouded in mystery. This quest moves beyond astronomical observation into the realm of particle physics, seeking the elusive particles that form this invisible scaffold. For decades, our understanding of the fundamental building blocks of matter and the forces that govern them has been encapsulated in what physicists call the Standard Model of Particle Physics. This highly successful theory describes all known elementary particles, such as electrons, quarks, and neutrinos, and three of the four fundamental forces: the strong nuclear force, the weak nuclear force, and electromagnetism. It has been rigorously tested and confirmed by countless experiments, including those at powerful accelerators like the Large Hadron Collider. However, the Standard Model, in its current form, offers no place for dark matter. None of its known particles possess the required properties to be stable, to have mass, and crucially, to interact only gravitationally and perhaps weakly without engaging with light. This means that if dark matter is composed of particles, they must be something entirely new, beyond our current established framework of particle physics. This realization propels physicists to propose and search for hypothetical particles that exist outside the Standard Model, venturing into uncharted territory. Could the greatest mystery of the cosmos lead us to discover an entirely new realm of particles beyond our most successful theories? Among the most prominent theoretical candidates for dark matter are weakly interacting massive particles, aptly abbreviated as WIMPs. The name itself provides a strong clue to their proposed nature. Weakly interacting suggests they would rarely, if ever, collide or otherwise engage with ordinary baronic matter, the protons, neutrons, and electrons that make up everything we can see and touch. This explains their invisibility. They do not interact with photons, the particles of light, meaning they neither absorb, emit, nor reflect any form of electromagnetic radiation. Consequently, they pass through stars, planets, and even our own bodies almost entirely unimpeded, like ghosts passing through walls. The massive part indicates that these particles are hypothesized to be relatively heavy, perhaps tens to thousands of times more massive than a proton. To put this into perspective, a proton has a mass of about 1.67 x 10^27 kilograms. A WIMP might be equivalent to a few dozen hydrogen atoms packed into a single invisible particle. Is it truly possible that trillions of these invisible particles pass through us every second, utterly undetected? The appeal of WIMPs extends beyond merely fitting the observational criteria for dark matter. There is a compelling theoretical argument, often referred to as the WIMP miracle, that lends them significant credence. This miracle arises from considering the conditions in the very early universe, just moments after the Big Bang, when the cosmos was an incredibly hot and dense soup of particles. In this primordial environment, WIMPs would have been produced in abundance, constantly colliding and annihilating with each other, much like matter and antimatter do. As the universe expanded and cooled, these annihilation reactions would have become less frequent, eventually freezing out, when the universe's density dropped below a critical point. Remarkably, calculations show that if WIMPs existed with masses and interaction strengths within a certain reasonable range, precisely the range needed for them to be weakly interacting, their leftover abundance from this early freeze-out process would naturally match the observed density of dark matter in the universe today. This elegant self-consistency, where the very properties that make them dark matter also explain their cosmic abundance, makes WIMPs a particularly attractive candidate. Many theoretical extensions to the standard model of particle physics, such as supersymmetry, naturally predict the existence of particles with WIMP-like properties. Supersymmetry, or SUSY, posits that every known particle has a heavier superpartner. For example, the electron would have a selectron, and quarks would have squarks. Among these hypothetical superpartners, the lightest supersymmetric particle, often called the neutralino, is a prime WIMP candidate. It would be electrically neutral, stable, and interact only via the weak force and gravity, perfectly fitting the description of a WIMP. The concept of supersymmetry itself is attractive to physicists because it could help unify the fundamental forces and solve other outstanding problems in particle physics, such as explaining the Higgs boson's mass. Thus, WIMPs are not just invented to solve the dark matter problem. They emerge naturally from broader theoretical frameworks aimed at a more complete understanding of physics beyond the standard model. However, WIMPs are not the only game in town. Another significant contender for dark matter's identity is the axion, a hypothetical particle with vastly different properties. Unlike the relatively heavy WIMPs, axions are theorized to be extremely light, perhaps 1 trillion times lighter than an electron, with masses in the range of microelectron volts, UeV. To grasp this scale, consider that a single electron has a mass equivalent to about 511,000 electron volts. An axion, therefore, would be almost infinitesimally tiny in comparison. Their interaction with ordinary matter would be even feebler than WIMPs, making them incredibly difficult to detect. Yet, despite their ethereal nature, they could collectively account for the universe's missing mass if they were produced in vast numbers in the early universe, forming a sort of cold, dense gas that permeates all of space. Could the solution to one cosmic enigma elegantly resolve another, seemingly unrelated puzzle from the quantum world? The theoretical motivation for axions stems from a completely different puzzle in particle physics, unrelated to dark matter initially. This is known as the strong CP problem. In quantum chromodynamics, the theory describing the strong nuclear force There is a term that could, in principle, allow for a violation of charge parity, CP, symmetry. If such a violation occurred, it would lead to observable phenomena, such as a measurable electric dipole moment for the neutron, meaning the neutron would have a slight separation of positive and negative charge. Despite extensive experimental searches, no such dipole moment has ever been detected, implying that this CP violating term is either zero or incredibly small. The Pecky-Quinn mechanism, proposed in the late 1970s, offers an elegant solution to this problem by introducing a new fundamental symmetry. When this symmetry is spontaneously broken, it gives rise to a new particle, the axion. Thus, axions are appealing because they offer a solution to two seemingly unrelated problems at once: the strong CP problem and the dark matter mystery. Because of their extremely low mass, axions would behave less like discrete particles and more like a classical wave or a coherent field across the universe, especially if they were produced cold in the early universe, meaning they had very low velocities. This cold dark matter property is crucial for explaining the formation of large-scale structures like galaxies and galaxy clusters, as slow-moving particles are more effective at clumping together under gravity. Axions, if they exist, would be constantly streaming through us, yet their interaction probability is so vanishingly small that detecting them presents an extraordinary experimental challenge, requiring highly sensitive instruments designed to pick up the faintest of signals. While WIMPs and axions represent the leading candidates, the scientific search for dark matter's true identity is broad and open-minded, considering many other possibilities. One such idea involves sterile neutrinos. Unlike the known active neutrinos in the Standard Model, which interact weakly and have extremely small but non-zero masses, sterile neutrinos would not interact via the weak force at all, only through gravity. They would be heavier than active neutrinos, but still much lighter than WIMPs. While some cosmological models could accommodate sterile neutrinos as a component of dark matter, their existence is not as strongly motivated by other physics problems as WIMPs or axions. Current experimental searches have significantly constrained the possible mass range for sterile neutrinos, and no definitive detection has yet been made. Another intriguing, though now largely disfavored possibility once considered, was that dark matter might consist of primordial black holes. These are hypothetical black holes that could have formed in the very early universe, perhaps within the first second after the Big Bang, from extreme density fluctuations. Unlike black holes formed from collapsing stars, primordial black holes could theoretically range vastly in size, from subatomic masses to thousands of solar masses. While black holes are indeed dark, they don't emit light and interact gravitationally. Extensive observational constraints have largely ruled out primordial black holes as constituting a significant fraction of the universe's dark matter. Gravitational lensing surveys, observations of gamma-ray backgrounds, and studies of stellar dynamics in dwarf galaxies have placed strict limits on their abundance across a wide range of masses. It is still possible they contribute a tiny, negligible fraction of dark matter, but they cannot explain the overwhelming majority of it. Crucially, these black holes would be made of ordinary baryonic matter compressed to extreme densities, which conflicts with the evidence suggesting dark matter is non-baryonic. Could the universe be even more exotic, holding a diverse zoo of dark particles, each playing a different role? The hunt for the true nature of dark matter particles defines a major frontier in modern physics, pushing the boundaries of both theoretical modeling and experimental design. The stakes are incredibly high, a discovery would not only solve one of the most profound mysteries in cosmology, but would also necessitate a fundamental revision of the Standard Model, opening up an entirely new chapter in our understanding of the universe's deepest laws. It means discovering new particles, new forces, and perhaps even new dimensions or symmetries that we can only glimpse through the gravitational effects of this pervasive, invisible substance. The quest is a testament to humanity's relentless curiosity and our capacity to infer the unseen from its subtle, yet undeniable influence on the grand cosmic stage. Whether it is a WIMP, an axion, or something entirely unforeseen, the answer promises to reshape our scientific worldview in fundamental ways. Having accumulated compelling evidence for dark matter's gravitational presence, seeing its invisible hand-shaped galaxies and the cosmic web, the scientific community embarked on an even more ambitious quest to directly detect or even create the elusive particles themselves. This evidence, however, only tells us that dark matter exists and how it interacts gravitationally. It doesn't tell us what it is made of, or what fundamental particle could be responsible for such a profound cosmic influence. To answer that question, scientists around the globe have deployed a network of sophisticated experiments, each designed with breathtaking precision to uncover the true nature of this phantom skeleton of the universe. This hunt for the universe's hidden components is one of the most challenging and ambitious endeavors in modern science, pushing the boundaries of technology and human ingenuity to their absolute limits. How do scientists hope to find something that doesn't interact with light and passes through everything? One of the primary avenues in this grand search is known as direct detection. Imagine, for a moment, trying to catch a ghost. You can't see it, you can't touch it, but you know it's there because things keep moving around. Direct detection experiments are essentially ultra-sensitive traps designed to register the incredibly rare instance when an invisible dark matter particle, theorized to be a weakly interacting massive particle, or WIMP, directly collides with an atom within a detector here on Earth. The weakly interacting part is crucial here. It means these particles rarely, if ever, bump into ordinary matter. Most dark matter particles are expected to pass right through our planet, and indeed through us, without leaving a trace. Detecting one such interaction is akin to finding a single, almost imperceptible whisper in a world of constant, overwhelming noise. To even stand a chance of hearing that whisper, these experiments must be shielded from every other possible sound. The Earth's surface is constantly bombarded by cosmic rays, high-energy particles from space that could easily mimic a dark matter signal, creating what is known as background noise. To filter out this overwhelming cosmic interference, direct detection laboratories are built deep underground, often thousands of meters beneath mountains or within disused mines. Picture cavernous spaces meticulously carved out of solid rock, some as deep as 2,500 meters, which is about 1.5 miles below the surface. Here, the sheer weight of the overlying rock acts as a natural, impenetrable shield. This subterranean isolation reduces the background noise from cosmic rays by many orders of magnitude, creating an environment of almost pristine silence, allowing for detectors of exquisite sensitivity to operate with minimal disturbance. What extraordinary lengths must humanity go to, simply to hear the faintest whisper of the unseen? Within these shielded underground sanctuaries sit the detectors themselves, often massive tanks filled with ultra-pure materials, meticulously chosen for their ability to respond to a minuscule energy transfer. Common choices include noble gases like liquid xenon or liquid argon, cooled to cryogenic temperatures, or supercooled germanium crystals. These materials are chosen because their atoms are relatively heavy, increasing the chance of a WIMP interaction, and they are inherently very pure, minimizing internal background radiation. The fundamental principle is straightforward, yet its execution is incredibly complex. When a theoretical WIMP particle traveling through space and then through the Earth happens to strike the nucleus of an atom within the detector material, it imparts a tiny amount of kinetic energy. This energy transfer causes the nucleus to recoil, much like one billiard ball hitting another. This recoil, though minute, can generate a detectable signal. What kind of signal would this be? Different detectors look for different phenomena. Some materials, like liquid xenon, will scintillate, producing a tiny flash of light. This light is then captured by highly sensitive photodetectors, which convert the light into an electrical signal. Other materials might ionize, meaning the recoiling nucleus knocks off a few electrons from surrounding atoms, which can then be drifted through an electric field to create a measurable current. Still others might generate phonons, tiny vibrations or heat pulses that can be detected by ultra-sensitive thermometers, cooled to temperatures just a fraction of a degree above absolute zero. Modern detectors often combine several of these detection channels simultaneously, allowing scientists to cross-reference signals and better distinguish a potential dark matter interaction from residual background events, such as radioactive decays from minute impurities in the detector materials themselves. The challenge is immense. Discriminating a single faint flash or tiny electrical pulse caused by an invisible particle from countless other mundane events. Imagine trying to hear a single, minuscule ping in a vast, silent chamber. How do scientists distinguish a WIMP from all other whispers? These detectors are not small or simple. The Xenont experiment, for example, located beneath Italy's Gran Sasso mountain, utilizes 5.9 metric tons of liquid xenon. The LLux Zeppelin LZ experiment, deep in a former gold mine in South Dakota, employs 7 metric tons of liquid xenon. These are immense, carefully purified vessels, kept at temperatures of approximately 100 degrees Celsius, 148 degrees Fahrenheit, for xenon. The sheer scale and precision involved are breathtaking. Imagine trying to keep a swimming pool-sized volume of liquid perfectly still and ultra-pure, then listening for a single, almost imperceptible ping within it, perhaps once a year, or even less frequently. Despite years of operation and ever-increasing sensitivity, these direct detection experiments have yet to yield an unambiguous detection of a WIMP. However, each non-detection is not a failure. Instead, it continuously refines our understanding, setting ever tighter limits on dark matter's possible mass and interaction strength, systematically ruling out regions of the theoretical landscape where dark matter could reside. Does the continued silence from these colossal detectors suggest dark matter is even more elusive than we imagined, or something entirely different? While direct detection aims to catch dark matter in the act of interaction, another major approach, known as indirect detection, seeks evidence of dark matter's annihilation or decay in the vastness of space. The idea here is that if dark matter particles, particularly WIMPs, are their own antiparticles, they might occasionally collide with each other and annihilate, converting their mass into pure energy, just as matter and antimatter particles do. This energy would then materialize as observable standard model particles, such as high-energy gamma rays, elusive neutrinos, or even antimatter particles like positrons and antiprotons. It's like looking for the smoke from a fire you can't see, knowing that the fire itself is hidden from direct view. If dark matter particles annihilate, what celestial beacons would betray their ghostly presence? Where would such annihilations or decays be most likely to occur? In regions where dark matter is most densely concentrated. The prime suspects are the centers of galaxies, including our own Milky Way, where gravitational simulations predict a dense halo of dark matter. Dwarf spheroidal galaxies, small satellite galaxies orbiting larger ones, are also excellent targets because they are incredibly rich in dark matter relative to their visible matter, and they generally lack complex astrophysical processes that could produce confusing background signals. Galaxy clusters, the largest gravitationally bound structures in the universe, also represent vast reservoirs of dark matter, making them promising hunting grounds for these telltale signatures. One of the most promising signals to search for are high-energy gamma rays. These are the most energetic form of light, far beyond what our eyes can see. Space telescopes, such as NASA's Fermi Gamma Ray Space Telescope, tirelessly scan the cosmos, mapping the distribution of gamma ray sources across the sky. If dark matter particles were annihilating, they would produce gamma rays with a very specific energy signature, a sharp spectral line that would stand out from the continuous, broad spectrum produced by other astrophysical sources like pulsars or supernovae, ground-based observatories like HESS, high-energy stereoscopic system in Namibia, MAGIC, Major Atmospheric Gamma Ray, Imaging Cherenkov on La Palma, and Veritas, Very Energetic Radiation Imaging Telescope Array System. In Arizona, also look for gamma rays by detecting the faint blue flashes of light, called Cherenkov radiation, produced when high-energy gamma rays strike the Earth's atmosphere. While intriguing excesses have been reported, particularly from the galactic center, none have yet been conclusively linked to dark matter annihilation, with alternative astrophysical explanations, such as populations of rapidly spinning neutron stars, remaining plausible and actively debated. Beyond gamma rays, scientists also search for neutrinos and antimatter particles. Neutrinos are incredibly elusive, almost massless particles that interact even more weakly than WIMPs, making them extremely difficult to detect. Gigantic neutrino observatories, such as IceCube at the South Pole, embed thousands of optical sensors deep within the Antarctic ice, transforming a cubic kilometer of ice into a giant detector. They look for the faint flashes of light produced when a neutrino rarely interacts with an ice molecule. If dark matter annihilations produce neutrinos, these observatories might register a subtle excess from dense dark matter regions. Meanwhile, spaceborne detectors like the Alpha Magnetic Spectrometer, AMS-02, mounted on the International Space Station, meticulously measure cosmic rays, specifically looking for an excess of positrons, anti-electrons, or antiprotons at certain energies, which could also be a signature of dark matter annihilation. Again, while some anomalies have been observed, the immense challenge lies in unequivocally ruling out conventional astrophysical sources like pulsars, which can also produce these particles through various high-energy processes. How can we be certain that a cosmic ray or a gamma ray burst isn't simply a mimic, rather than the true signature of dark matter? The third major front in the dark matter hunt takes us not deep underground or into space, but to the cutting edge of particle physics, powerful particle accelerators. The most famous of these is the Large Hadron Collider, LHC, at CERN, located near Geneva, Switzerland. Unlike direct and indirect detection, which are passive searches relying on nature's processes, colliders actively attempt to create dark matter particles under controlled laboratory conditions. The fundamental principle at play is Einstein's famous equation, E=mc², which tells us that energy can be converted into mass. By smashing particles together at extremely high energies, we can momentarily recreate conditions similar to those just moments after the Big Bang, potentially creating new, heavier particles that weren't present before the collision. Could the most powerful machines ever built by humankind finally create the very particles that hold the universe together? At the LHC, protons are accelerated to nearly the speed of light, reaching 99.999999991% of the speed of light, and then collided head-on. These collisions generate incredible bursts of energy, far exceeding anything naturally occurring on Earth. If dark matter particles, such as WIMPs, are heavy enough to be produced at these energies, they might briefly flicker into existence. However, because these particles are theorized to interact only weakly with normal matter, they would immediately pass through the massive, multi-story detectors surrounding the collision points without leaving a trace. So, how do scientists detect something that leaves no trace? They look for what's missing. Imagine two billiard balls colliding on a perfectly frictionless table. If you precisely know their initial momenta, their mass times their velocity, you can predict the momenta of the balls after the collision. If one of the balls suddenly vanished, the total momentum would no longer balance. In a particle collider, physicists precisely measure the energy and momentum of all the visible particles created in a collision. If a dark matter particle were produced, it would carry away some of this energy and momentum, escaping the detector unseen. This missing energy, or missing transverse momentum, would be the telltale signature of a new, weakly interacting particle. It would be like trying to balance a meticulously kept budget, but realizing a significant chunk of money has simply disappeared without a trace. A clear sign that an unknown factor is at play. How do you detect something that leaves absolutely no trace, only hinting at its existence through a profound absence? The challenge, of course, is that other known particles, like neutrinos, also escape detectors unseen, carrying away momentum. Scientists must meticulously analyze millions upon millions of collisions, looking for statistical excesses of missing energy that cannot be explained by known physics. Many theoretical frameworks, such as supersymmetry, SUSY, predict the existence of WIMP-like dark matter candidates, often referred to as neutralinos. The LHC is also actively searching for these hypothetical supersymmetric partner particles. If found, it would not only validate supersymmetry, a theory that suggests every fundamental particle has a heavier superpartner, but also potentially identify the particle nature of dark matter. To date, the LHC has not definitively produced dark matter particles or their supersymmetric partners, but it continues to set ever tighter constraints on their possible masses and interactions, systematically ruling out regions of the theoretical parameter space, guiding future experiments. As these particle smashers refine their search, are we slowly cornering dark matter, or merely revealing the vastness of our ignorance? This global, multi-pronged approach, direct detection deep underground, indirect detection in the vastness of space, and creation attempts in powerful accelerators, underscores the scientific community's unwavering commitment to unraveling the dark matter mystery. Each method has its unique strengths and weaknesses, and together they form a complementary network of probes, each pushing the boundaries of what's detectable. the lack of a definitive discovery so far is not a failure. Rather, it is a constant refinement of our understanding, forcing scientists to consider new possibilities and to develop even more sensitive instruments and innovative theoretical models. It implies that dark matter might be even more elusive, or its nature more exotic than initially hypothesized, perhaps requiring even more extreme conditions or novel detection strategies. What deeper understanding of reality awaits us should humanity finally unlock the secret of dark matter? The journey to identify dark matter is a profound testament to human curiosity and scientific perseverance. It involves some of the most advanced technology ever conceived, requiring international collaboration on an unprecedented scale. From the pristine silence of underground laboratories to the dizzying complexity of particle accelerators and the cold vacuum of space, scientists are relentlessly pursuing this invisible component of our universe. Every null result, every refined limit, pushes the frontiers of knowledge, guiding the next generation of experiments and theories. It's a slow, painstaking process, but one that promises to fundamentally reshape our understanding of the cosmos and the fundamental laws that govern it, revealing an entirely new sector of reality that has remained hidden in plain sight. After decades of dedicated research, the existence of dark matter is no longer merely a hypothesis. It stands as a cornerstone of our current cosmological model. It is a fundamental ingredient, an undeniable presence that shapes the cosmos, knitting together the vast tapestry of galaxies and clusters. Without it, the universe we observe, from the delicate spin of a solitary galaxy to the sprawling architecture of the cosmic web, simply could not exist in its present form. Our understanding of the universe, codified in the highly successful Lambda CDM model, hinges critically on the presence of this invisible substance. Lambda, representing dark energy, drives the accelerating expansion of the universe, while cold dark matter, or CDM, provides the gravitational scaffolding that allowed structures to form in the first place. Could the fate of the entire cosmos, its ultimate end or endless expansion, be written in the properties of this invisible substance? Imagine the universe in its infancy, just a few 100,000 years after the Big Bang. It was a hot, dense, and remarkably uniform plasma, a cosmic soup of protons, electrons, and photons. In this early, turbulent environment, ordinary matter, known as baryonic matter, was tightly coupled with light. The intense pressure from photons prevented baryonic matter from clumping together significantly, smoothing out any nascent density fluctuations. It was like trying to build a sandcastle on a constantly shifting, vibrating surface. However, dark matter, by its very nature, did not interact with light. It was immune to these radiative pressures. While baryonic matter was still sloshing around, unable to form stable structures, dark matter could begin to coalesce under its own gravity. These initial tiny overdensities of dark matter acted as gravitational seeds. They were the first whispers of structure in an otherwise featureless cosmos. Over millions of years, these dark matter clumps grew larger, slowly drawing in more dark matter through their persistent gravitational pull. They formed invisible halos, vast, diffuse spheres of dark matter that permeated the early universe. As the universe continued to expand and cool, eventually reaching an age of about 380,000 years, the temperature dropped sufficiently for electrons and protons to combine, forming neutral hydrogen atoms. This event, known as recombination, decoupled baryonic matter from light. Suddenly, ordinary matter was free to fall into the existing gravitational wells created by the dark matter halos. This is the crucial moment when the universe's structure began to solidify. The dark matter halos became the gravitational anchors, pulling in the now free baryonic matter. Gas began to accumulate within these halos, eventually collapsing under its own gravity to ignite the first stars and form the first galaxies. Over cosmic time, these smaller dark matter halos merged, forming larger and larger structures, creating the vast, interconnected network we call the cosmic web. Picture it as an immense invisible skeleton, spanning billions of light years, where galaxies are like luminous pearls strung along its unseen filaments, and galaxy clusters represent the bright knots where these filaments intersect. The voids between these structures are not truly empty, but are regions where dark matter is much less dense, having been gravitationally drawn away towards the filaments and clusters. Without dark matter to provide these initial, stable gravitational anchors, the universe would likely be a much smoother, less structured place, devoid of the intricate galactic tapestries we observe today. Imagine a universe where none of these luminous structures exist. What would our cosmos look like without its silent architect? While dark matter's role in the grand cosmic narrative is unequivocally profound, its practical applications in our daily lives might seem less apparent. We cannot yet harness its energy, build engines powered by its interactions, or use it to transmit information across vast distances. It remains a phantom, interacting with our world almost exclusively through the subtle, yet powerful tug of gravity. There are no immediate technological spin-offs that allow us to improve our navigation systems, enhance our communications, or mitigate space hazards in a direct, tangible way. It is not a resource to be mined or a fuel to be burned. However, to dismiss dark matter's significance based solely on its lack of immediate utility would be to profoundly misunderstand the nature of scientific inquiry and its long-term impact. The pursuit of dark matter is not about building a better gadget. It is about comprehending the very fabric of reality at its most fundamental level. Its existence challenges the standard model of particle physics, the most successful theory describing the fundamental particles and forces that govern our universe. If dark matter particles exist, they represent an entirely new class of matter, demanding an expansion of our current understanding, potentially revealing new forces and interactions beyond our present knowledge. This quest pushes the boundaries of human intellect and ingenuity, forcing us to ask deeper questions about the universe's true composition. Does the true value of discovery lie only in practical application, or in the profound expansion of our understanding of reality itself? Furthermore, understanding dark matter is crucial for predicting the ultimate fate of the universe's destiny, whether it will continue to expand indefinitely, eventually succumb to a big rip as dark energy tears everything apart, or perhaps even reverse course in a big crunch, is intimately tied to its total mass energy density. Dark matter contributes a substantial portion to this density, influencing the gravitational forces that oppose or complement the expansion driven by dark energy. By precisely measuring the amount and distribution of dark matter, cosmologists can refine their models, allowing us to peer into the distant future and glimpse the ultimate cosmic destiny that awaits everything within it. It's a fundamental piece of the cosmic puzzle that determines the final chapter of existence itself. The ongoing, tireless search for dark matter's true nature continues to drive remarkable innovation across experimental physics and astrophysics. The sheer difficulty of detecting a particle that interacts so weakly with ordinary matter demands unprecedented levels of precision and technological advancement. Consider the direct detection experiments, buried miles beneath the Earth's surface in cavernous laboratories, shielded from cosmic radiation by tons of rock and water. These facilities are engineering marvels, designed to create environments of extreme quiet and purity. Scientists work with ultra-cold, ultra-pure materials like liquid xenon or germanium, cooled to temperatures just a fraction of a degree above absolute zero. Every vibration, every stray cosmic ray, every minute trace of radioactivity must be meticulously accounted for or eliminated. This pursuit pushes the limits of cryogenics, material science, vibration isolation, and radiation shielding, leading to breakthroughs that find applications in other fields, from medical imaging to quantum computing. What unseen breakthroughs in technology and engineering are born from the relentless pursuit of the invisible? Similarly, the indirect detection efforts, scanning the cosmos with powerful telescopes, require cutting-edge instrumentation. New generations of gamma-ray observatories, like the Fermi Gamma Ray Space Telescope, and future instruments, are designed with enhanced sensitivity and resolution to pinpoint potential dark matter annihilation signals in regions like the galactic center or dwarf galaxies. The development of these sophisticated detectors, capable of distinguishing faint astrophysical signals from potential dark matter signatures, requires advancements in sensor technology, signal processing, and spaceborne electronics. Even the particle accelerators, like the Large Hadron Collider, constantly push the frontiers of energy and luminosity, necessitating breakthroughs in superconducting magnets, vacuum technology, and complex data analysis algorithms to sift through quadrillions of particle collisions for the faint signature of missing energy that could betray a dark matter particle. This relentless pursuit of the unseen promises to reveal entirely new particles and forces, extending our understanding beyond the familiar confines of the standard model. Imagine the profound implications if a WIMP or an axion were definitively detected. Such a discovery would not merely add a new entry to the particle physics lexicon. It would fundamentally reshape our understanding of matter, energy, and the very laws that govern the universe. It might confirm theories like supersymmetry, suggesting that every known particle has a heavier superpartner, or validate the Pequet-Quinn theory, which elegantly solves a long-standing puzzle in quantum chromodynamics, while simultaneously predicting the existence of axions. But the potential revelations might be even grander. Some theories propose the existence of an entire dark sector, a parallel universe of particles and forces that interact primarily with each other and only weakly with our familiar matter, perhaps through a dark photon or a dark Higgs boson. This concept opens up a truly mind-bending possibility that our visible universe, with all its stars, planets, and life, is merely one component of a much larger, more intricate cosmic machinery, and that the vast majority of its constituents operate in a realm almost entirely separate from our own. The detection of dark matter could be the first step towards unveiling this hidden cosmos, revealing a universe far richer and more complex than we currently dare to imagine. Could our familiar universe be just one luminous island within a much vaster, hidden cosmos, teeming with entirely different forms of matter and energy? The mystery of dark matter remains one of science's most profound and exciting challenges. It is a testament to the scientific method's power that we can deduce the existence of something we cannot see, touch, or directly interact with, purely through its gravitational influence on the visible universe. We have journeyed from Fritzwicky's initial, almost overlooked calculations of missing mass in the Coma cluster in the 1930s to Vera Rubin's meticulous and compelling observations of galactic rotation curves in the 1970s, to the powerful evidence provided by gravitational lensing, the bullet cluster, and the cosmic microwave background. Each piece of evidence has tightened the net around this elusive substance, moving it from a speculative idea to an indispensable component of our cosmic model. Yet, despite this wealth of evidence, the identity of dark matter remains a vast unknown. We still don't know what it is made of. Is it one type of particle, or many? Does it interact with itself in ways we haven't considered? Are there dark forces mediating these interactions? These are the questions that fuel countless research programs worldwide, driving the development of next-generation instruments like the Vera C. Rubin Observatory, which will map billions of galaxies and provide unprecedented data on the distribution of dark matter through weak lensing, and the Euclid mission, designed to precisely chart the geometry of the dark universe and the growth of cosmic structures. Future upgrades to underground detectors and particle accelerators are also on the horizon, pushing the sensitivity and energy frontiers even further. The enduring mystery of dark matter reminds us of the vast unknowns that still await discovery beyond our visible reality. It underscores the humility inherent in scientific exploration, the recognition that even with our most powerful telescopes and most sophisticated theories, there is still so much more to learn. It is a call to continued curiosity, a beacon guiding us toward new frontiers of knowledge. The universe is not just what we can see, it is also what we can infer, what we can deduce, and what we can imagine. And in that vast, unseen realm, dark matter stands as a silent, invisible architect, a phantom skeleton that holds the cosmos together, patiently waiting for humanity to finally unravel its deepest secret. Perhaps as you drift peacefully into sleep, pondering the silent